Hi, Assalamualaikum and welcome back to my channel Physics from 5 KSSM. Today I want to continue 2.5 Archimedes Principle Part 1. In this video I will discuss on learning standards. The first one describe the relationship between buoyant force and the difference in liquid pressure at different depths for a submerged object. The second one relate the balance of forces with the state of flotation of an object in a fluid. Let's look at this concept. Plasticine P and Q of same mass are placed in container with water. Plasticine P sinks while plasticine Q floats on the surface of water. Let's look at the situation of the plasticine P and Q. First in P, the shape is in solid shape, but plasticine Q is in hollow shape. So how does this situation occur? If we look at the mass, both have same mass, of course, same weight. But why the solid shape sinks, but the hollow shape floats? So this situation actually can be explained by two concepts. The first one, we can consider the concept of density, because we already know that object which is less dense will float in denser liquid. So let's look at the explanation. The hollow shape of plasticine Q has larger volume as compared to the solid shape of plasticine P. For same mass, density of the hollow shape is smaller as compared to the solid shape. Thus, the hollow shape floats at the surface. So due to its average density becomes smaller due to larger volume of the hollow shape. Let's look at the concept of force. Both plasticine has same weight. Plasticine Q experience larger force which able to support its weight. Plasticine P experience smaller force that cannot support its weight. What is that force? What is the force that able to support the weights of the plasticine Q? The force that we are going to discuss in this topic is known as buoyant force or upthrust. So we can say that for plasticine P, buoyant force able to support the weight of plasticine Q. Thus, it floats. For plasticine P, buoyant force is too small to support the weight of the plasticine due to its solid shape. Thus, it sinks. Okay, let's discuss further about this topic on buoyant force. When an object immersed either fully submerged or partially submerged in liquid, it will experience upthrust or buoyant force. So what is the meaning of buoyant force? Buoyant force is the force acting upwards on an object immersed in liquid when there is pressure difference between the lower surface and the upper surface of the object. Let's look at this one. This is a cylinder fully submerged in a liquid. The lower surface is at depth of H2. The upper surface or top surface is at depth of H1. Thus, the height of the cylinder is equals to H2 minus H1, or we just can denote as H. The surface area of both surface, the top surface and the bottom surface, is A. Let's derive the formula for buoyant force. We have discussed before the concept of pressure. I hope you still remember pressure in liquid. For the top surface, the pressure we can label as P1. We can determine it by using the formula pressure in liquid, if you still remember, rho GH. Because of the top surface is at depth of H1, thus we get P1 equals to rho GH1. Rho is density of the liquid. Force acting on the top surface, F1, can be determined by pressure P1 multiply surface area, P1A. Thus we got rho g a h1. Now let's look at the bottom surface. For the bottom surface, pressure at the bottom surface equals to rho g h2. Thus, the force on the bottom surface F2 equals to P2 times surface area E. Thus, we get rho GA H2. If you look at the value of H, H2 is longer than H1. Thus, the force F2 is larger than F1. So the difference in force at top and bottom surface, or the difference in pressure, it will produce a net force upwards. Thus, resultant force that acts on the cylinder F equals to F2 minus F1. Okay, what we do, we just factorize rho GA, thus we get H2 minus H1. H2 minus H1, actually height of the cylinder, we can represent it by H. Thus we get resultant force F equals to rho GAH. The product of A and H, surface area and height of the cylinder, is equals to volume of the cylinder. Thus, we can substitute AH with V. So we get the resultant force equals to rho GV. The resultant force upwards will support the weight of the cylinder so that the cylinder will float in liquid. Thus, buoyant force F equals to rho GV. Okay, so this is the formula that we can use to determine buoyant force. We have derived the formula for buoyant force FB equals to rho GV. Rho is density of liquid, G is gravitational acceleration, and V is volume of liquid displaced. So in this activity, we are going to find the relationship between buoyant force and weight of liquid displaced. From the formula of density of liquid, we get mass of liquid displaced equals to density of liquid displaced multiply volume of liquid displaced. The volume of liquid displaced is equals to volume of the object submerged in liquid. Okay, let's assume there's a volume of water in a beaker. Put one finger so you can see the level of water rises slightly. Now place two fingers. You can see it rises more. When you place four fingers, you can see the level of water rises insignificantly and some of water displays out from the beaker. So actually this activity is done by Archimedes. Archimedes observed that certain amount of water displays out from the tub. The same situation when you place four fingers into the beaker water. Let's assume that an object floats in water. Why the object able to float? Because there is a force that supports the weight. This one stated by Archimedes Principle. The buoyant force applied by the fluid is equals to weight of liquid displaced. We can carry out this activity. Suspend an object by using a spring balance. Record the reading of the spring balance. And there's a water in the beaker which has a spout, and then you put some water until the same level as the spout. Now immerse the object, fully immerse in the liquid. You can see certain amount of water will be displaced out into the beaker. Record the reading of the spring balance. Now we can weigh the weight of the water in the beaker. The weight of the water displaced in the beaker is equals to buoyant force. According to Archimedes Principle, when an object is immersed fully or partially in a fluid, the upward force applied by the fluid on the object is the same as the weight of fluid displaced by the object. So the volume of water that displaced by the ship is equals to the volume of the submerged part of the ship. Buoyant force equals to rho gv equals to rho vg, rho v coming from the formula m, mass, okay, or formula of density. Density equals to m divided by volume. Thus, m equals to rho v. So from the formula of buoyant force, rho gv, if we rearrange the formula, so we get rho vg. Rho v we can substitute as m. If rho here is density of liquid, volume here is volume of liquid displaced, thus m here is mass of liquid displaced. So the product of mass of liquid displaced and G is equals to weight of liquid displaced. Thus we get this relationship. Buoyant force equals to weight of liquid displaced. So this relationship can be proved by experiment that will be carried out in the lab. So this one actually the simplest way to state Archimedes principle. Okay, so buoyant force equals to weight of liquid displaced. Okay, let's look at this experiment 2.3. You can refer to your textbook. So this experiment is to relate between buoyant force and weight of liquid displaced. Inference: buoyant force depends on weight of liquid displaced. Hypothesis: the greater the weight of liquid displaced, the greater the buoyant force. To determine relationship between buoyant force and weight of liquid displaced. Manipulated variable, weight of liquid displaced. Corresponding variable, buoyant force. Constant variable, density of liquid or water in this case. Apparatus, slotted weights, eureka can, beaker, spring balance, electronic balance, retort stand, and wooden block. Material is water. Look at the arrangement of apparatus. So we have this one, the first situation. Use spring balance, hang the slotted weight, and record the reading. So in the eureka can here, put some water until it's about to pour out from the spout here. Okay, so meaning the maximum water that can be placed in the spout here. And then we have an empty beaker. Weigh the empty beaker and record the mass. And then next, immerse the slotted weight, fully immersed in liquid. You can see the water will spurt out from the spout here. And record okay, mass of the water displaced in the beaker. Okay, so what we do, this is the method or procedure. Hang 100 grams slotted weights on the spring balance. Record weights of slotted weight in the air, WE in table 2.6. Place the beaker on the electronic balance. Reset the reading of electronic balance to 0. Immerse the slotted weight fully into the water. Record weight of slotted weight in water, WW. Calculate the buoyant force, FB equals WE minus WW. From the reading of electronic balance, calculate weight of water displaced, WD. Assume 1 kilogram is 10 Newton. So this one just follow. Actually, we use 9.81, but just follow instruction. Repeat steps 2 to 5 using slotted weight, mass 200, 300, 400, and 500 grams. So we can record all the readings. First, you weigh in air the weight of the slotted weight for 100 grams. So if change to Newton, you will get equals to 1 Newton. And then weight when immersed in liquid or water, record as 0.8. From there, we can calculate weight of water displaced. So we can record weight of water displaced by weighing the amount of water that spurt out from the eureka can. So we get 0.20, okay, Newton. Okay, how to get this buoyant force? Buoyant force actually is the difference in weight. Weight in air, WE, minus WW. So we get 0.20. Okay. Okay, and then you can repeat the step by 200 gram, 300 gram, 400 gram, and 500 gram. So until we get 5 set of readings. Okay. So from the 5 set of reading, we want to find the relationship between weight of water displaced and buoyant force. That's why we use this data. Okay. So we don't use mass of slotted weight or weight of slotted weight to plot the graph. Okay, we use these two physical quantity, weight of water displaced and buoyant force, because that one is our hypothesis. Okay. Okay, plot a graph of WD against FB. So this is the graph that produces a straight line passes through the origin. So based on the graph, state what conclusion that we can get from the graph. Okay. The conclusion is WD is directly proportional to FB. Okay, we can see the graph just now, directly proportional to WD directly proportional to FB, or a straight line pass through origin. Okay, discussion. What is value of gradient of the graph? To determine gradient, we draw a triangle below the line. Calculate 0.6 divided by 0.6, we get 1. No unit because WD is Newton, FB also Newton, so we get 1. Okay. Now state relationship between buoyant force and weight of water displaced based on the result of experiment. From the result experiment, the ratio of WD to FB actually is gradient. We have calculated here gradient equals to 1. Thus we get WD equals to FB. So from this result or the graph that we get, we can conclude that buoyant force equals to weight of liquid displaced. So we have proved the Archimedes principle by using this experiment. Look at example 1. The same situation as the experiment carried out. So we have a spring balance, hang a piece of stone in air, and the reading recorded is 0.67 Newton. Then immerse the same stone into water, fully immerse. Water will displace out from the eureka can and record. Okay, by using this weighing scale. The spring balance shows reading 0.40 Newton. The weight in air is known as actual weight, W1. The weight when the object immersed in liquid is known as apparent weight, W2. Okay. Why there is weight loss? The weight loss actually represents buoyant force FB. Thus, buoyant force equals to actual weight W1 minus apparent weight W2. So W1 minus W2 equals to FB. Okay, now look at the reading of the weighing scale here. According to the value that calculated from here, we get buoyant force equals to 0.67 minus 0.40. Okay, so we get 0.27 Newton. Mass of empty beaker is 0.10. So weight of the beaker is 0.10 Newton. Weight of the water displaced and the weight of the empty beaker is 0.37. Thus, the weight of the liquid displaced equals to 0.37 minus 0.10. So we get the same value, 0.27. So from here also we can prove that buoyant force equals to weight of water displaced. Okay, example 2, the same situation. Okay, weight in air 25 Newton. When immersed in liquid, you can see the amount of water displaced as compared to original level. So weight of stone in water 50 Newton. So in this case, loss of weight is 10 Newton. Thus, buoyant force equals to 10 Newton. So weight in air 25 Newton minus weight in water 50 Newton. So we get loss of weight, or known as buoyant force. The state of flotation of an object in fluid depends on the value of force that acts on the object. Let's look at the first diagram. Let's say the object partially immersed and float at rest, or the object fully immersed also float at rest. So in this case, forces are balanced. W equals to Fb. Weight of the object equals to buoyant force. So in this case, resultant force equals to 0 or balanced force, thus object is stationary. Okay, look at the second picture. Let's say object is moving down or accelerate down. In this case, weight is greater than buoyant force. This one will produce resultant force downwards, or in this case, forces are unbalanced. So this one will cause object move downwards with an acceleration E, and it will sink down until the forces balance again. So in this case, W is greater than Fb. Okay, let's look at this one. The object accelerate up. So in this case, resultant force upwards. Forces are unbalanced. Object move upwards with an acceleration E. It will accelerate up, and finally it will stop when the forces balance again. Okay, so this one is state of flotation, depends on the situation of object. Either the forces act on the objects are balanced or not. Let's look at one example, a ship. A ship that immerses, the part that immerses in liquid, the section of ship below the sea level will displace water. The force that act on the ship, there are two forces, buoyant force and weight of the ship. This one, float or partially immerse. For the case of the fish here, it fully immersed but still floats because buoyant force equals to its weight. Forces acting on the ship are in equilibrium. Resultant force on the ship is 0. Hence, weight of the ship equals to buoyant force. Based on Archimedes Principle, buoyant force equals the weight of water displaced. Thus, weight of the ship equals to weight of water displaced. How about the volume of water displaced? Volume of the seawater displaced equals to volume of the section of the ship immersed in seawater, meaning the volume of the part which is below the sea level, this part only. So if you want to determine the volume of the liquid displaced for the object which is partially immersed, so the volume of the water displaced or liquid displaced is equals to volume of the submerged part only. For the case of fully immersed, like a fish here, volume of the liquid displaced equals to volume of the object, because the whole object immersed in liquid. Okay, so you must be able to differentiate between these two cases. Either the object is partially immersed or fully immersed. Okay, let's look at this question. An object is hung from a spring. The reading on the spring balance in air is 65 Newton. When immersed in liquid, the reading becomes 30 Newton. So what is buoyant force on the object in water? This is, we already discussed before. Buoyant force equals to W1 minus W2. Actual weight minus apparent weight. So we get 65 minus 30, we get 35 Newton. What is weight of water displaced by object? Remember what we discussed before, the relationship? Buoyant force equals to weight of liquid displaced. From the first part here, we already calculated buoyant force equals to 35 Newton. Thus, we also can say that weight of liquid displaced equals to 35 Newton. This is what's stated by Archimedes Principle. Look at C. Determine the volume of water displaced by the object. Density of water 1000 kilogram meter to the power negative 3. From the formula of buoyant force, Fb equals to rho GV. V is the volume of water displaced equals to buoyant force divided by density of liquid and divided by G. So in this case, G we use 9.81. So 35 divided by 1000 times 9.81. Thus we get 3.56 times 10 to the power negative 3 meter to the power negative 3. So this one is the volume of water displaced by the object. Okay, D. What is the volume of the object? Look at this case. Is this partially immersed or fully immersed? Okay, we have discussed before. Volume of liquid displaced equals to volume of the submerged part of the object. In this case, object is fully immersed. Thus, we can say volume of the object equals to volume of liquid displaced for fully immersed object. So from here, we can get the volume of object equals to 3.56 times 10 to the power negative 3 meter to the power negative 3. So no need to calculate again if you know the concept. You know how to relate between all the values that we have discussed before. Okay. So that's all my video for this